Hello, I'm Seul Lim, a second-year dental student at Dan국 University. Today, I'm going to present a research paper titled Viscoelastic Properties, Creep Behavior, and Degree of Conversion of Bergfield Composite Resins. This paper was published in 2015 in the journal Dental Materials. The research was a collaboration between the School of Dentistry at the University of Athens and the Material Science and Biomedical Engineering departments at the University of Wisconsin. Before we go into the study, let's first take a look at what Berg-field composite resins are. These are like cured dental composites that can be placed in 4 to 5 mm increments, which is thicker than traditional composites. They are designed to save time and reduce the risk of voids between layers. But since we place them in Berg, it's important to evaluate how well they cure and how strong they are. Traditional composites are placed in 2 mm layers to ensure full curing, but this takes time and can introduce air bubbles. Berg-field composites aim to cure deeper layers at once. However, we still need to carefully assess their mechanical properties and curing depths to make sure they are clinically safe. The purpose of this study was to evaluate the viscoelastic properties, creep behavior, and degree of conversion of Berg-field composites under different conditions. The researchers began with the null hypothesis, which stated that there would be no differences among the materials in terms of mechanical properties and degree of conversion, and that these properties would not be affected by testing conditions. The goal was to test this assumption and see if material type or environmental factors had any impact. A total of 7 Berg-field composite resins were tested. They can be divided into two categories. First, the flower-based type. These are low viscosity materials that require a top capping layer. First example, SDR, SD, very flowable with high conversion but lower strength. And second example, Venus Berg-field VE has the lowest filler contents, making it less strong. Extra base XB, strongest among the flowers due to its higher filler content. And second category, the restorative type. This can be used alone to fill cavities. First example is sonic fill SF, activated by sonic vibration to reduce viscosity temporarily. A second example, tetric Evostrom Berg-field TE, uses a special photoinitiator for deeper curing. And extra fill XF has the highest filler content and the strongest mechanical properties. Lastly, EverX posterior is not flowable but still used only as a base. It contains glass fibers that improve strength and recovery. Samples were tested under 4 conditions. First condition is dry at 21 Celsius degree. And second, wet at 21 Celsius degree. And third, wet at 37 Celsius degree is to simulate body temperature. And first condition, wet at 50 Celsius degree to simulate brief exposure to hot food or drink. This helped simulate real oral environments. Specimens were 1 mm thick and 80 mm long. Each was light cured in sections using an LED curing unit. The testing device used a Helmholtz coil and a permanent magnet attached to the sample. When electric current was applied, the magnet created a torque. A small laser beam was reflected off a mirror on the sample and projected onto a screen to measure displacement. This setup allowed precise measurement of angular deformation under torque. 4 tests were performed. First, static testing measured shear modulus G and flexural modulus E. Second, dynamic testing used sinusoidal forces to calculate storage modulus G1 and loss tangent, tangent delta, and dynamic viscosity. Third, creep testing applied torque for 3 hours, then recorded recovery for 50 hours. Fourth, degree of conversion %dc measured at top and bottom surfaces using ATR FTIR. Let's look at the results of static and dynamic testing. XF had the highest shear and flexural modulus, while VE had the lowest. In general, the presence of water and higher temperature reduced mechanical properties in all materials. Flowable materials were more sensitive to these changes and showed lower strengths. In dynamic testing, similar trends were observed. Higher filler content led to stronger performance. Let's look at the result from the creep test. This graph shows the amount of strain over time for each composite material during a 3-hour torque application. As we can see, flowable materials like SDR and extra base showed the largest deformation. They continued to strain more as time passed, which means they have lower resistance to long-term stress. In contrast, restorative materials like sonic fill and extra fill had much smaller strain values. This means they can resist constant stress much better, making them more suitable for posterior restorations. Ever X posterior also showed strong performance similar to restorative types, likely due to its fiber reinforcement. This table shows the elastic recovery of each material after removing the torque and letting it rest for 50 hours. Restorative types like SF and XF recovered almost completely, showing values close to 100%. That means they returned to their original shape after the load was removed, a good sign for long-term durability. On the other hand, flowers like SDR and extra base had lower recovery values. They couldn't return fully to their original shape, which means permanent deformation could occur in clinical use. These results show that while flowers are easy to handle, they are not ideal for high-stress areas unless used with a stronger capping layer. Let's look at the result of degree of conversion %dc. SDR and VE had the highest degree of conversion, while XF had the lowest. All materials showed lower conversion at the bottom surface. The decrease was smallest in SDR and VE, meaning they cure better at deeper levels. Now, let's talk about the Pierce correlations. At the top surface, there was no significant correlation between filler content and degree of conversion. But at the bottom, there was a significant negative correlation, R equal minus 0.80. This means that materials with more filler cured less at the bottom because the light couldn't penetrate as well. Now, let me briefly discuss the main findings and what they mean in a clinical context. First, regarding mechanical properties, restorative type work fields like extra fill and sonic fill showed high strengths, making them suitable for stress-bearing areas. In contrast, flower-based materials such as SDR and Venus had lower stiffness and should not be used alone. Extra base, however, was an exception among the flowers because of its high filler content, about 70%. Second, on temperature and moisture effects, our composites became weaker as temperature and moisture increased. Water acts like a plasticizer, softening the material and reducing stiffness. Third, creep behavior. Flowers like SDR and extra base showed large deformation on the load and poor recovery. On the other hand, restorative materials like Sonifill and extra fill showed better elastic recovery. Using a flower base with a capping layer significantly improved creep resistance, which is essential for long-term clinical durability. First, degree of conversion. SDR and Venus had the best curing depths with high percent DC even at the bottom. Extra fill had poor conversion at depths due to its opacity and high filler content. There was also a negative correlation. The more filler, the lower the bottom percent DC. Finally, in terms of clinical implications, Flower-Berg fills must always be used with a capping layer in posterior teeth. Restorative Berg fill can be used alone, but we must ensure proper curing depths. Overall, material selection should balance both mechanical performance and curing efficiency. To wrap up, here are the key takeaways from this study. First, Flower-Berg fill composites showed excellent curing efficiency, even at 4 mm thickness. However, they had weaker mechanical properties, so they must always be covered with a conventional composite layer, especially in posterior restorations. Second, restorative Berg-fill composites had much better strength and creep resistance, but their curing depth was more limited, which means light doesn't penetrate as deeply. So, for thick restorations, we need to be cautious about the depth of cure. Third, material selection should always be a balance between curing efficiency and mechanical performance. We also need to consider the location of the restoration, whether it's in the anterior or posterior region, and the amount of stress it will receive. Finally, the clinical recommendation is simple. Perfect composites are time-saving and effective materials, but for long-term success, it's important to use them properly, especially by applying the correct layering technique based on the material type. Thank you for listening.